Howdy, my name is Reagan Sizemore, and today we are going to explain conditional probability, Bayes' rule, and how to apply these concepts to solve real-world problems. So what is conditional probability? Conditional probability is essentially a measure of the probability of an event happening on condition that another event has also happened. Conditional probability says that the probability of A conditional upon B is the probability of A if we can assume that B holds. A quick reminder that is worth noting is that there is no requirement that B actually holds in this situation. So, from this information, we can write the conditional probability as P A slash B, which we read as the probability of A conditional upon B. If you look at the Venn diagram, you can see we have a sample space S with individual probabilities A and B. Since we are interested in A conditional upon B, we are only interested in the relationship between the A and B region of the space and the B region of the space. Further, how do we calculate conditional probability? Well, the formula follows from the information we just went over. When the probability of B is greater than 0, the probability of A conditional upon B can be calculated by dividing the probability of the conjunction of A and B by the probability of B. You may wonder why the probability of B needs to be greater than 0, and this is simply because you cannot divide anything by 0, and in calculating conditional probability, you must do exactly that. So, following from conditional probability, we have Bayes' rule. Bayes' rule is a consequence of the definition of conditional probability, and essentially gives us a way to invert or reverse a conditional probability. So if we wanted to find the probability of A conditional upon B, and we start with the knowledge of the probability of B conditional upon A, Bayes' rule gives us a way to obtain the probability of A conditional upon B by inverting the probability of B conditional upon A. This may sound a little confusing, but it is actually very simple. Take, for example, we have a hypothesis and evidence that supports that hypothesis. Usually we assume the truth of a hypothesis when forming our evidence. This can be represented as the probability of E conditional upon H. But what we really want to know is whether or not our hypothesis is true based on our evidence. And this can be represented as P H slash E, or the probability of H conditional upon E. And this is exactly what Bayes' rule allows us to do. So, in conclusion, Bayes' rule is designed to solve a problem of inverse probability.
Hi, I'm Christian Call, and I'll explain the different types of probabilities used in Bayes' rule, then apply it to a problem, and finally solve it. Bayes' rule is a formula that combines different kinds of probabilities to help us calculate how likely something is after we've seen new evidence. The rule is written like this. The probability of the hypothesis given the evidence, that's P of H given E, equals the probability of the evidence given the hypothesis times the probability of the hypothesis divided by the total probability of the evidence. Each part of the formula has a specific meaning. P of H is the prior probability. That's how likely we thought the hypothesis was before seeing any evidence. P of E given H is called the likelihood. It's the chance of seeing the evidence if the hypothesis is true. P of E is the total probability of the evidence, how likely that evidence is, no matter what caused it. P of H given E is the posterior probability. It's what we're solving for, the updated chance of the hypothesis being true after we've seen the evidence. These four probabilities work together to help us reason more accurately and help us figure out the cause of something we've already seen happen. Now, let's apply Bayes' rule to our specific problem. Cynthia was randomly given one of three software programs, and her program crashed. Now we're trying to figure out which program she most likely was using. First, we'll look at what we know. 6 people were assigned red, 3 got orange, and 1 got blue. That means Cynthia had a 60% chance of getting red, 30% chance of orange, and 10% chance of blue. Each software also has a different crash rate. Red crashes 10% of the time, orange 20, and blue 30. To use Bayes' rule, we need the overall probability that any program crashes, so we multiply each software's chance of being assigned by its crash rate. That means any program crashing at all happens, according to our formula, 15% of the time. Now, let's figure out the big questions. What's the chance Cynthia was using blue, given that her program crashed? According to our formula, it's a 20% chance she had blue. And for red, it's a 40. So even though blue crashes more often, red is more likely the one Cynthia used, because more people were using it. That's what Bayes' rule helps us figure out. Not just likelihood, but how likely something is once we've seen what happened. Now that we've used Bayes' rule to set everything up, here are our final results for Cynthia's crash. First, the probability that Cynthia was assigned blue, given that her program crashed, is 20%. Second, the probability that she was assigned red is 40%. This might seem surprising at first because blue actually has the highest individual crash rate at 30%, compared to red's 10%. But Bayes' rule shows us that we can't just look at how often something crashes, we also have to look at how common each program was to begin with. In this case, most employees were assigned red, while only 10% were assigned blue, so even though blue crashes more often per person, there were just way more people using red. This means overall, it's still more likely that a random crash like Cynthia's came from red instead of blue. This is why Bayes' rule is so powerful for real-world problem solving. It helps us avoid jumping to conclusions based on one piece of information. Thank you.